Welcome back to the channel, Tech Enthusiasts. Today, we're diving into another groundbreaking topic in artificial intelligence: transformers. These powerful models have revolutionized the way machines understand and process data, enabling breakthroughs in natural language processing, computer vision, and beyond. We'll explore what transformers are, how they work, and their transformative applications across industries. So let's get started. Transformers are a type of neural network architecture that has become the backbone of modern AI systems. Introduced in the landmark 2017 paper Attention is All You Need, transformers have since become the foundation for models like GPT, BERT, and T5. Unlike traditional models that process data sequentially, transformers use a mechanism called self-attention to analyze entire datasets at once, making them faster and more efficient. To understand this better, let's use an analogy. Imagine you're reading a book. Instead of reading one word at a time, you glance at the entire page and focus on the most important words or phrases. Transformers do something similar. They analyze all parts of the input data simultaneously, identifying relationships and patterns that might be missed by sequential models. This allows them to understand context and generate highly accurate outputs. At their core, transformers rely on two key components. The first is the self-attention mechanism, which allows the model to weigh the importance of different parts of the input data. For example, in a sentence like "the cat sat on the mat," the model might focus more on cat and mat because they're central to the meaning. The self-attention mechanism calculates a score for each word in the sentence, determining how much attention it should pay to other words. This enables the model to capture long-range dependencies and relationships within the data. The second component is positional encoding, which ensures the model understands the structure of the input. Since transformers don't process data sequentially, they use positional encoding to keep track of the order of words or data points. For example, in the sentence "the cat chased the dog," the order of words is crucial to understanding who is doing the chasing. Positional encoding adds information about the position of each word, allowing the model to process the data in a way that respects its structure. Once the input data is processed through these components, the transformer generates an output that captures the relationships and context within the data. This makes transformers incredibly powerful for tasks like language translation, text generation, and even image recognition. The applications of transformers are as diverse as they are revolutionary. In natural language processing (NLP), transformers power models like GPT-4 and BERT, enabling applications such as chatbots, translation tools, and summarization systems. For instance, chatbots like ChatGPT use transformers to generate human-like responses by understanding the context of a conversation. Similarly, tools like Google Translate use transformers to map words and phrases between languages with high accuracy. Summarization systems, on the other hand, can condense long articles or documents into concise summaries, saving time for readers. In computer vision, transformers are being used to analyze images and videos. For example, models like vision transformers (VITs) can recognize objects, classify images, and even generate captions for photos. This is particularly useful in fields like healthcare, where transformers can analyze medical images to assist in diagnostics. For instance, a transformer-based model could examine an X-ray or MRI scan, identify abnormalities, and provide a detailed report to assist doctors in making accurate diagnoses. Beyond these applications, transformers are increasingly being employed in industries such as finance, where they help detect fraudulent activities by analyzing transaction patterns, and in supply chain management, where they optimize logistics by forecasting demand and improving inventory control. In education, adaptive learning platforms leverage transformers to provide personalized feedback and recommendations, tailoring the learning experience to individual students' needs. For example, an AI-powered tutor could analyze a student's writing and offer suggestions for improvement, or recommend resources based on their learning style and progress. As this technology evolves, its integration with other advanced AI systems will unlock even more possibilities. Researchers are working on multimodal transformers, which can process multiple types of data, like text and images, simultaneously. For example, OpenAI's CLIP model uses transformers to connect images with textual descriptions, enabling applications like generating images from text prompts. Another exciting development is the use of transformers in speech recognition and audio processing, where they can analyze and generate human-like speech with remarkable accuracy. For instance, AI-powered transcription services can now convert spoken language into text with near-human precision, even in noisy environments. However, transformers also raise important ethical considerations. One major issue is bias. Since transformers are trained on large datasets, they can inherit biases present in the data. For example, a language model might generate biased or offensive content if the training data contains such examples. Addressing these biases is critical to ensuring fair and ethical AI systems. Researchers are actively working on techniques to detect and mitigate bias in transformer models, such as using diverse training datasets and implementing fairness constraints. For instance, datasets are being curated to include more balanced representations of gender, race, and culture to reduce bias in AI outputs. Another challenge is computational cost. Transformers require massive amounts of data and computing power to train, making them resource-intensive. Training a large transformer model like GPT-4 can cost millions of dollars and consume significant energy. Researchers are working on techniques like model distillation and efficient architectures to make transformers more accessible and sustainable. For example, model distillation involves training a smaller, more efficient model to mimic the behavior of a larger transformer, reducing the computational resources required. Emerging innovations like sparsity in transformers, where only relevant parts of the model are activated during computation, further enhance efficiency. Additionally, advancements in quantization, reducing the precision of the model's calculations, are helping to make transformers more energy efficient without sacrificing performance. The future of transformers is incredibly promising. From powering intelligent chatbots and recommendation systems to advancing healthcare and creative industries, transformers are at the heart of modern AI. As technology continues to evolve, transformers will play an even bigger role in shaping the future of intelligent systems. Imagine a world where AI-powered assistants can understand and respond to complex queries, where medical diagnoses are faster and more accurate, and where creative professionals can collaborate with AI to push the boundaries of art and design. Moreover, as we address their limitations and refine their capabilities, transformers will become a pivotal force driving innovation and societal progress in ways we are only beginning to imagine.